Joining us on the Open Alliance show will be 2996 Cougars Gone Wired. You got to check out everything they've been working on. This team so much to talk about from their CAD side and their prototyping side as well too. But wow, is there just a ton to go into in regards to what they're doing for their custom object detection as well. And well, you're going to get a full trig lesson. So if you're into that, you can't wait to jump into everything they've been doing from how their object detection works, the math behind it as well too. Cougars Gone Wired, a team that has consistently been performing well. We can't wait to see how they do this year. So let's learn more about their progress coming up here on the Open Alliance show. This video on fun is brought to you by viewers like you and also in partnership with the following. Discover how Kettering University students engineer their success with Kettering's amazing co-op employment programs where students earn great pay and gain valuable experience. Those accepted into Kettering University can apply for a robotics scholarship, providing up to an additional $5,000 a year in tuition assistance. Head on over to kettering.edu/first to learn more and apply. Here on the Open Alliance show, we're going to welcome in to 996 Cougars Gone Wired coming in from Colorado. I hope you've been taking a look at their OA blog. Lots of fantastic things that we'll be jumping into, including their game strategy. We have some prototypes we're going to be talking about, CAD the show on screen, and a lot to dive into with programming. Three fantastic students are here from 2996 talk more about it. So if you don't mind, students, can you introduce yourselves? Let us know what you do on your team, and we'll hop right in.
Hi, I'm Jeremiah. I'm our VP of Programming. I kind of manage and direct our programming sub-team.
I'm Riley. I am our VP of Community Outreach, but I'm also our head scout, so I manage a lot of our strategy during competition.
Hi, I'm Kellen. I'm our VP of Manipulator, so I handle all parts of the robot that handle manipulating the game piece. So this year, that's our intake and our shooter, along with our transfer system.
Well, we're bringing you in just a few weeks in already, so we got a little bit to catch up on to figure out what your team's been working on. So let's jump into game strategy. Give us a little bit of breakdown on what direction you move forward with and why you moved forward in those directions too.
Yeah, so our strategy actually doesn't begin at kickoff. It begins a couple months before when we decide on our robot goal. And what we do there is we basically decide what we want to accomplish with our robot. And this year we decided we had two goals. Number one was to be the number one highest scoring robot based on scouting data at our competitions. And secondly, a bit of a joke, but kind of serious considering some of our past experiences in playoffs, we wanted to get past match 13. So we want to be at least a finalist at our two regionals.
That's noble goals for sure.
Oh yes, it's been fun figuring out how we can design a robot around that, but it's been cool. So then once we get into our strategy, that's where we take that robot goal and we're like, so how can we achieve that goal within this game? So this year, looking at Crescendo, we saw Speaker, Amp, and Trap and Climb as our kind of the main ways to score. And pretty much right away, we said Speaker, a definite, we need to do that. And then afterwards, the debate was kind of between the Trap or the Amp, doing one or the other. And after looking at levels of difficulty and all that, we decided 100% Amp and no Trap, because the Trap is posing a lot of difficulty to teams already, and so we felt that was a good decision. And beyond that, we decided that we want our robot to be small and light, so we want to be able to go under the stage and just generally be a very fast mover, very fast cycler. And also, we really want to prioritize that auto, because it's 5 points for each game piece that is scored. And definitely, since we're not doing the Trap, we want to be able to make up for that with a very high scoring auto. And of course, Climb. We figured that's definitely something we want to do. And beyond that, really the philosophy behind it was not doing everything, because we've found a lot in the past where if we go into a season saying we want to do everything, like we did last year with Charged Up, we basically said we want to pick up a piece from any orientation in every location. We want to place it everywhere. We ran into a lot of trouble and saw that it was just outside of our skill range.
Let's go a little bit into the robot architectures that you decided to move forward with, and then we have a lot of cool stuff in regards to prototypes to talk about as well.
Yeah, so we always start off our season just doing a lot of brainstorming. You can see some remnants of it still on our whiteboard. But basically starting off just trying to figure out literally every single possibility. We filled up the entire whiteboard just conceptualizing as many different ways that you could realistically going about that. And then through more research, more detailed design and then just thinking through all the parts, discussing what would be most optimal, what would kind of not really be. So kind of dismissing Catapult because of like just throwing the note around, seeing how it goes. And then we used CAD this year, which was a really cool resource that we got to learn. It kind of led us, you can see it on screen, to 5 main basic breakdowns, all based around a wheel launcher. We saw very early success from our own team and a lot of other teams. And then through prototyping and testing, we kind of narrowed down the specifics of what kind of shooter we want to have. So the real big difference, we knew we wanted to have an over bumper intake. We discussed an under bumper intake, but decided we really wanted to go with a known system that we had our own experience with and that we knew we would be able to integrate. And an under bumper was a bit more ambitious, and we wanted the intake to be a relatively simple, guaranteed mechanism. So then a lot of the discussion was about what we needed the shooter to be able to do. We very quickly decided variable angle. We wanted to make sure that in different distances from the speaker, whether it's up to the subwoofer or all the way at the wing line, or even maybe even the center line, depending on how well we're able to dial in our shooter and how accurate it's able to get, we knew we wanted to have that control over angle. So then the bigger thing was, are we able to shoot into the amp, or do we want to shoot down into the amp? Because that changed what the shooter would need to be able to do. And we didn't want to just make that huge design. So like some of the designs were just like a low shoot up into it, have a very low, simple design. And then one of the more complex ones was having your whole shooter on a large arm so that you could either shoot up into it or down into it. And all of the designs basically centered around that. So we decided, why make a guess on that? Let's just test it. So we have part of our team builds a practice field. That's part of our students. It's a really cool thing that that group of kids get to do. So they assembled an amp really quickly in week 1. And using one of our initial shooter prototypes, we just tested shooting up and deflecting off the top, shooting up, arcing in, and then also holding it above and shooting down. And we saw pretty quickly, and also from other OA teams, that it's definitely viable to shoot up and down into the amp, and you could definitely dial that in. But we decided on a robot goal that because the amp isn't worth a lot of points, but it requires a lot of cycling in order to get that, we wanted our amp to be 99% accurate. Like, we did not want to miss any shots into the amp because it's just too big of a hit into your cycle time. So while shooting up into it was consistent, or you were able to do it for sure, we wanted to guarantee that. So that meant going down, which basically sent us very fairly quickly into, we wanted to shoot down into it. So we were going to put our shooter on a wrist and then have that on a pivot arm so we can get down, but then still have a very consistent wrist mechanism directly transferring from our over bumper intake.
Going from CAD into some prototypes as well too, can we bring up a few different prototype options you've gone with? And then after that, we'll take a look at more of your full CAD as well too with that.
Oh, okay. So we quickly split our prototyping into 2 main groups and then divided those groups even more. So we knew we were going to have a shooter of some sort. And so the big question with that was wheels on the side, kind of similar to either the kitbot or having the wheels on both sides, and then also like if you need to have multiple of those, and then also like a top bottom shooter, which is what we ended up going towards. But then along with that, we also tested, inspired by Team 95 Grasshoppers, a slanted axle to add spin. And then later our top bottom led us into having a split axle setup so that you can control your left and right at different speeds, which will let you shoot the note with spin. And then we've also been testing some other stuff with only having the wheels on one side and also spin. And what we really saw just with our early prototyping is that the wheels, the horizontal wheels just on the side of the note, we definitely were able to get it to work. We spent almost a full week developing that prototype with a ton of different variations of wheels, different setups, different motors and power, and having like a second wheel or just the wheels on the side and some compression zone. And we were able to get it working pretty well. And we decided like we could definitely get that to work at shorter distances. But part of our strategy that we wanted to have the option to do, whether or not we actually end up doing in matches, we'll have to see, but is the stashing based strategy where from the source, we can like shoot into our corner and then shoot several during the amplification period. That was slightly lowered by the team update that reduced how many notes you could score during amplification, but it's still something we want to leave our options open to. along with the possibility of shooting from the wing line and maybe even the center line, all depend on how accurate we can get our shooter, but it's options we wanted. And we really saw with the horizontal that you just got a much lower output in your note compared to how much you put into it. So even we were using 2 vortexes on that setup, which were very nice for prototyping, but even running them at really high RPM, we kind of hit a maximum because you lost a lot of your energy into deforming the note into compressing. And then when it sprang back out, it lost a lot of accuracy. So then one of our other prototypes was just having wheels on the top and bottom. Originally was just 2 full rollers. And we saw immediately that one had a much higher output. And we also saw something we were concerned about is that during competition, you have a large variation in, of course, the wear of the note. This is just through fairly mild prototyping and gets worn down a lot compared to a new note. They have very different levels of compression and they rebound very differently. So with the horizontal, you compressed it a lot on the sides. And that meant the more that these changed, the more your accuracy would be hindered. So especially when we're aiming for some really high autos this year, we're concerned that not having the control over that and varying like throughout a match even what compression you have, we decided that having a narrower compression zone on the top bottom would be more efficient. And it had a higher power output as well. But problem we saw with it, and that many other teams that tested top bottom saw, was that you didn't get any spin from the note. And that was okay at short distances. If you put enough power into it, it launched fairly effectively. But at range, what would happen, sometimes like if you threw a Frisbee just straight on, it just kind of hits dead zones and it loses accuracy really quickly. So it'll fly and then just kind of lose control or drop to the ground. So we quickly switched from testing horizontal and top bottom to testing how to add spin to a top bottom setup. So we tested slanted axle, inspired by Team 95. We tested split axle, and that's what our current design is based around, is having 4 independently driven motors, or 4 different independent wheels, and then running the left side and the right side at different speeds. And that gives us a lot of control over how much spin we get, which has been really good for testing. And something we very much believe in is not locking yourself into a final design too early and leaving yourself open for modularity. So by having a fully disconnected axle setup, it gives us control over left-right spin along with different top and bottom levels if we want to experiment with different like upward and downward arcs. So it's nice using this kind of setup. We don't have to lock ourselves into that decision this early. And it's also just had a lot of really good results of a consistent compression range, a high power output, but also getting that spin. So that's kind of what led us into deciding that it's what we wanted to use as our final design.
How about from intake-wise? Which direction have you gone for that?
Yeah, so we did a lot of testing and prototyping with our intakes. Largely like how many bars we needed, what kind of materials worked, what kind of spacing works. We did a lot of really rapid prototyping at the beginning. I think we went through at least 15 versions in the first like 4 days of prototyping, just using scrap wood, drilling holes in it, seeing what worked, making adjustments. And that led us to getting really consistent geometry that we liked. Something we feared was lack of control of the note as we transferred it, that if we were like launching in the robot, we weren't able to hit that transfer. So with this design, you can show it. This is our current final geometry. And then it also includes on the back of our shooter, we'll have some funnel plates that will basically, we've done more testing with the vectoring of the note as well, something we were really concerned about because this note behaves really strangely. It's very different than any game piece I've ever worked with, and that a lot of people have realized that like an issue encountered when doing that was like it doesn't behave as a single piece. Like if you push it into if you try to funnel it, it doesn't slide. It just kind of squeezes, and we're having issues of it like bouncing out. And so what we ended up realizing is there were like 2 main approaches to it. And then one that I've seen a lot of other OA teams testing is having like your funnel plate be basically like a conveyor belt, like passive rollers. And we tested that and it definitely worked, but it was more complexity and harder to integrate than what we would have liked. But what we realized is by having the top 2 rollers on our intake have low grip, so the note's able to slide in it. What happens is if you have a funnel plate, it basically hits it and then rotates around it and into your shooter with really high consistency, and it's just passive funnels. So if we can show you that on our current CAD design, or that we.
It's not crashing. It was not crashed.
So we have a very tight handoff zone because we needed to maximize the length of our arm in order to get down into the amp. So we only have it's really like 1.5 inches between our frame and our shooters. We needed to get a very tight funnel. And that's what we found to be the most effective and the most reliable for that. So we have our bottom rollers are just 2 pieces of hex with surgical tubing stretched over it, which has been performing really well for a small form factor, but having a lot of grip. And then the top are just plain hex at the moment. We might investigate using other materials that'll be a little more impact resistant, but we've really liked how small we were able to get this. It's very compact, but has a lot of control and is able to get that funneling that we want.
Yeah, so right now, now that we kind of decided on some final designs, the CAD isn't obviously done yet. As you can tell, there's some pieces floating around. It's not done. But the big deadline for us as compared to other teams is that most, at least the sheet metal parts that you see on this robot, such as the shooter, the pivot arms, and battery mount, even stuff as simple as that, we don't manufacture those. Pretty much our biggest sponsor since the beginning of our team back in 2008, a local machining company called Vertec, has graciously offered to always machine out our parts every single year. So that gives us a strict deadline of yesterday to finish the CAD. But luckily, we finished all the stuff in the CAD that needed to be sent to them, though we do not have the ability to manufacture. But the benefits of that is that it gives us a lot more time to test. So we have less manufacturing time in exchange for more testing time, which helps us a lot.
We still manufacture some parts in-house. We have a CNC that we use for a lot of polycarb pieces, and that's what our intake currently is and will be made out of, because something we've realized throughout our team's history is you definitely want your intake to be compliant. Really, any mechanism outside your robot. After 2020, we had a sheet metal intake that ended up being a bit squiggly. So, and since then, we've been using either polycarb or HDPE as our intake plates, and that's been amazing for being able to withstand a ton of impacts and still be fine. Along with, we'll have some other side panels and some parts of the shooter are machined in-house along with all tube components. So we still get to have an amazing educational opportunity for our students of learning how to use some of those machines and doing that. Then we're able to do some really complex parts, and some of these sheet metal parts are very complex and lets you a lot of things thanks to that sponsor.
All right. I want to make sure we get programming enough time. Everything you've been going through is fantastic. I love seeing your overall design and the way it's gone, but I want to make sure we get programming enough time as well, too. Let's jump into programming, what you've been working on, and what some of your objectives and goals are for the Crescendo season from programming.
All right. So this season, some of our biggest goals have really been implementing our use of vision. In prior years, it's always been we want to do it. We had code for it and then never got fully tested. This year is different, however. We've made significant progress in getting the use of our Limelight and April tags for pose estimation of a robot, as well as an OpenCV pipeline for detecting notes, not only in the view of a camera, but actually relative to the robot from that camera's detection. And also having potentially dynamic autos. Can't think of a better way or a more descriptive way of putting it, but essentially variable auto paths depending on potentially like the state of the field. So for example, we are trying to get a note from the center line, but for whatever reason, either another team is also grabbing that note and got there before us. If that note's not there, instead of just thinking it's there, trying to get it, going and finding the next closest note to us and grabbing that instead of wasting that cycle during auto. Because in auto this year, having every single note scored in the speaker, basically being the equivalent of an amped speaker shot, is kind of significant. So part of that involves being able to detect notes autonomously with our robots, which actually I have a little demo of this. So we have a fresh note that we put, very fresh note. Basically, this one is pulled directly out of the box. You can see basically each step in our process for getting the actual shape of the note and also detecting it. And if you'll notice in that bottom right window, there is the center point marked with an XY meters. And so that is the actual physical location of the note relative to the camera, which ended up only being some simple trig. But real quick, just to show how robust this pipeline is, with a horribly damaged note from our
Well prototyped.
questionably a note, no. It is still capable of fully detecting it and able to completely identify it, approximate where it is, for the most part without any issue. And actually, the most surprising part about this was being able to detect where in like real space the note is. Surprisingly, wasn't actually that complicated. It ended up just being a bit of trig from, sorry. It ended up being basically trig from the camera's starting location, its angle, and instead of treating each pixel as a way of measuring distance, if you treat it like an increment in the angle of your view, it ends up working a lot nicer. So I actually have basically the math behind what is going on with estimating that location. This is in Desmos because math is beautiful. So the center point is basically representing the location of our camera. It's at a set height. We have the number of pixels horizontal and vertical, which is this pixel Y and pixel X. We have the height of the camera from the ground, as well as the angle of the camera and the horizontal and vertical field of view for the camera in degrees. From those values, we also basically calculate the increments in angle for each pixel in terms of the horizontal and vertical angle. It makes more sense when looking at the actual vector that is pointing away from the camera, where I have this slider over here, which is basically saying I think this one, yeah, this is the X pixels. So as I increase it, move it more towards the side, it ends up changing in the direction that vector is pointing at. And same goes for vertical. So you may notice that it is actually, the view of the camera is actually a trapezoid, which is why the measurement, or using pixels as like a measurement of distance, gets a little messy, because each pixel isn't a set like distance increments. It's more so a change of angle, which is why this vector approximation of where you're looking at based off of the pixels works. But yeah, so instead of having to deal with this weird trapezoid shape where each pixel is somewhere between maybe a centimeter and potentially even a meter at certain angles, each pixel is just a set change in angle, and then you can just draw a line from wherever the camera's looking to that point, do a little bit of trigonometry, and you've found that point because you have two right angles, or two right triangles. So that's kind of where we're at with note detection. We plan on running this on a coprocessor that we'll have on the robot with a webcam attached. And then it's publishing the detections over network tables And in our GitLab repo, we have all of our source code. It's completely public. Basically, what this whole full vision pipeline is doing is it's detecting the contour for the note in the center point. Then we're figuring out where in space relative to the camera that note is, and then we can publish that X and Y values to network tables as well as the camera string using a camera server.
Well, Cougars Gone Wired, I didn't think I was going to get a trig lesson today, but thank you for that run through. No, this is awesome. I loved all the thought process that's going into your object detection. Make sure you go check out their GitHub. It's posted on the OA blog as well, too. So 2996 Cougars Gone Wired, wish you best of luck. You play week 2, so we can't wait to see your continued progress. So make sure you follow their blog for more. And guys, thanks a lot for taking the time. Good luck the rest of the way.
Thank you for
Thank you.
having us.
Thank you.
This video on fun is brought to you by viewers like you and also in partnership with the following. Discover how Kettering University students engineered their success with Kettering's amazing co-op employment programs where students earn great pay and gain valuable experience. Those accepted into Kettering University can apply for a robotics scholarship, providing up to an additional $5,000 a year in tuition assistance. Head on over to kettering.edu/first to learn more and apply. Don't forget to like, subscribe, and ring the bell to stay up to date on our new videos. Keep the conversation going and provide your input to our content. Watch our live shows at twitch.tv/firstupdatesnow. Join our Discord at discord.gg/firstupdatesnow and check out Fun FTC on Facebook, Instagram, and Twitter, and First Updates Now on Facebook, Instagram, TikTok, and Twitter.